Okay, so I've told you about Lagrangian spontaneous stochasticity. I've told you about Eulerian spontaneous stochasticity. And so what I want to talk about in this final lecture are various open questions and what I personally consider some of the interesting directions of research. And that is what we're going to end up with for this series. Okay, so first of all, let me talk about an obvious question is there a relationship between the two kinds of spontaneous stochasticity? Does one imply the other? How are they related? And so first of all, let me talk about, does Lagrangian spontaneous stochasticity imply Eulerian? The answer is no. We have counterexamples. The first counterexample is the Kryknon model, where this concept first arose. This is actually the same talk that Francesco showed us the other day. I wrote it in slightly different notation. This is the Kryknon model solution, which in fact was rigorously constructed first by Lejeune and Ramon using this Krylov-Varetnikov expansion. And in fact, it's known that this has unique, strong stochastic solutions. So that means that if I fix U and I fix my initial data theta 0, there's exactly one solution to that scalar advection equation. In that sense, there is no Eulerian spontaneous stochasticity for this scalar advection equation. Although there is Lagrangian spontaneous stochasticity in the sense that the characteristics of this velocity, which are the Lagrangian trajectories, are rigorously known to be stochastic. So there's the first simple counterexample, is that in this model you have Lagrangian spontaneous stochasticity, but you do not have Eulerian spontaneous stochasticity. Another counterexample is Berger's equation, and this is something that I worked out with. This was the very first thing that I did with Theo Drivas in 2014 when he arrived at Johns Hopkins. And Konstantin Ehr's representation applies not only to Navier-Stokes, but also to other equations, including Berger's. And so we could consider the limit of the stochastic Lagrangian trajectories in the Konstantin Ehr representation of the Berger's equation. And what you find is that when you take the limit in shock solutions, you do in fact get Lagrangian spontaneous stochasticity in the Berger's solutions with shocks, but it's a very simple variety. So as everybody knows, here I have a space-time diagram. Here I have my initial interval of Lagrangian particles, and they start to intersect on a shock line in space-time. So this direction is time, that's space. And when you go backward in time, you have Lagrangian spontaneous stochasticity in this model backward in time. And it's very simple. At every point on the shock, with probably 1/2, you go along the one characteristic to the left and the other one 1/2 to the right. Okay, so there is spontaneous stochasticity, and as we discussed in detail in this paper, it is that Lagrangian spontaneous stochasticity which is responsible for the anomalous dissipation in the shock. Okay, so it's also a really nice example of anomalous dissipation for an active scalar equation arising from spontaneous stochasticity. But the inverted Berger's equation for these shock solutions, there is a unique entropy solution. So there is no Eulerian spontaneous stochasticity in this model, but there is Lagrangian spontaneous stochasticity backward in time. By the way, it's known from many works, numerical works, primarily. I don't know of any experimental work on this, but there's asymmetry in Navier-Stokes turbulence also forward and backward in time. And Lagrangian particles separate faster back in time in three-dimensional turbulence than they do forward in time. The Berger's equation gives a very, very striking example of that asymmetry because you have splitting backward in time and only coalescence forward in time. So a complete asymmetry in the Berger's case. Okay, so in retrospect, the fact that Lagrangian spontaneous stochasticity doesn't imply Eulerian spontaneous stochasticity could already be expected from the well-known fact that you can get Lagrangian chaos in non-chaotic laminar Eulerian flows, even stationary Eulerian flows. And so you can have a nice, stable, steady state, smooth solution of Euler equation for which you get Lagrangian chaos. And so in some sense, this is like the rough version of that. So what about the other direction? Can you have Eulerian spontaneous stochasticity? Does that imply Lagrangian spontaneous stochasticity? Well, I'm stealing from what Vlad said this morning. In their model, in fact, we know that if you look at these different level M diffusion equations in the Armstrong-Vickel model, along different subsequences, you can converge to distinct weak solutions. If they converge to distinct weak solutions, that means that you had to have had different, and these different weak solutions will show anomalous dissipation, they had to have had different stochastic Lagrangian trajectories just from the Feynman-Katz representation. And in fact, this has been argued in a recent paper. This was the paper that Vlad was referring to. These authors have visualized their mathematical construction numerically. And they argued from this that that means that Eulerian spontaneous stochasticity in fact implies Lagrangian spontaneous stochasticity. So the one comment I would make about that is that can be at most what I called fragile spontaneous stochasticity. Because in that case, you would get different spontaneously stochastic trajectories for the same velocity field along different subsequences, and it would not be robust. It wouldn't be a unique set of trajectories. This work did raise an interesting possibility that they're actually in their preprint they call it level 1, but I don't think that's the appropriate thing to do if you're using Cauchy or large deviations language. It should really be called level 2 Lagrangian spontaneous stochasticity. They raised the interesting possibility that there might be a kind of level 2 Lagrangian spontaneous stochasticity in which you get non-unique limits. And so you get non-unique limits of these random processes on the particle paths, but there is a non-trivial random distribution on the probability distributions themselves, and that distribution on those probability distributions is unique. And so the way you can think of that is if you, for example, were coming from a Navier-Stokes solution, with some fixed deterministic initial data, I tried to convince you it's plausible in some cases that in the inviscid limit with also vanishing noise, you might get a spontaneously stochastic ensemble of Euler solutions. And then for each one of those Euler solutions, it's possible because they're sufficiently chaotic and mixing enough that you would have for every one of those one distribution of the scalar, but then that distribution over those random ensembles for the scalar would itself be universal. Okay, it's possible.
Like, you know, the authors, Rushnak and...
They're here.
Yes, they're here.
Okay.
You know?
Yes, I heard that they were talking to them before, but I'm embarrassed I don't know how to pronounce their name. And so therefore I wasn't going to say it. How do you pronounce it? Pardon? Rufinach? Okay. Oh, Simonet, yes, that one, but the first author was the one that caught me. So I didn't want to mangle your names, sort of. Okay. Okay. Okay, so that's an interesting possibility. By the way, also for general smooth solutions, and even in turbulent solutions, but at fixed Reynolds number, it has been argued, for example, by Giovanni Galavati in a number of interesting papers, but in particular this one, that there are certain kinds of relations between Lagrangian and Eulerian Lyapunov exponents. So you can look at the Euler equations. It's a non-canonical Hamiltonian system if you look at the velocity field alone. So it's given by a Poisson bracket and a Hamiltonian, but there are no canonically conjugate variables. But if you add to it the Lagrangian flow maps, then in fact it's canonical Hamiltonian. And so you have two different sets of dynamics, the whole flow map and also the velocity field. And Galavati has conjectured relationships between the Lyapunov exponents of those two parts of the dynamic. So there could be some intrinsic relationship between the Lagrangian flows, chaotic properties, and those of the Eulerian velocity field.
I have a question. What does it mean, and what is the interpretation of this probability distribution of these limit distributions?
Well, I mean, for example, if I'm solving the Navier-Stokes equation together with the passive scalar advection equation, and I look in the limit of high Reynolds number, one possibility would be that I would get an ensemble of solutions of the Euler equation. Each solution of the Euler equation would have spontaneously stochastic Lagrangian particle trajectories that would be unique for it, but then they would be different for the passive scalar depending on which Euler solution you were looking at, and then there would be a probability distribution over those Lagrangian particle paths for all the different Euler solutions. That's, yeah. So that means, when I took the limit, I would not get robust spontaneous stochasticity for the Lagrangian particle paths. I would get, different Lagrangian particle paths, but they would all be uniquely associated, for example, with one specific Euler solution. Possible.
And so in this case, does it give ideas how to show that since the Eulerian is older 1/3, you get Eulerian 1/2 for the Lagrangian trajectories?
Ask them.
I ask you.
I don't know. You've been asking me this for years. Well, I keep asking.
I will continue.
Okay. Okay, so here's another interesting question that arises in spontaneous stochasticity. It is presumably related to this old concept of eddy noise. This is an idea that's been around for a long time. In fact, Hasselmann was one of the first people to raise this concept of stochasticity in climate models. This paper was one of those that was cited in his Nobel Prize. This wasn't the main work, but he did several different things, including wave turbulence and a variety of other things. This idea was also carried up by a paper by Harvey Rose for passive scalar and talking about subgrid scale modeling. He argued that in addition to an eddy diffusivity, there should also be an eddy noise. I recommended this paper to Vlad a while ago. Okay. And then Chuck Leith carried up on this. And so you might imagine that there should be some relationship between these concepts. And in fact, in a paper that I wrote in 1996, carrying over Wilson-style coarse graining methods, I had argued that it should be true in turbulent flow that you should have vanishingly small noise that would lead to effective, large-scale, robust stochastic dynamics that are independent of the particular kind of noise. This was before the concept of spontaneous stochasticity had appeared by about a year. And I didn't make much progress on this at all. But in fact, you do suspect that there is a connection. Okay, so Scott, this is for you. Okay? So now we're going to consider spatial coarse graining, okay, and the effective subgrid modeling, okay? And the answer is, in fact, you can get robust stochastic large-scale models out of spontaneously stochastic situations. And here I'm going to tell you a little bit about some work on this that I've been doing with my PhD student, Lowen Peng, who's supposed to graduate this summer. He worked with me on the infinite Reynolds number limit of the Landau-Lifshitz equations, and this is another chapter in his thesis. And so we decided to take the Arnold cat map problem of Malayabov and Rebekis and try to modify it a little bit to make it more like the Kelvin-Helmholtz problem. because ultimately we would like to understand some effective large-scale stochastic dynamical model for this problem. And the idea, again, is that in these problems you would expect that if you not only look at long times, like I discussed in the case of the renormalization group theory for that simple minimal model, the ODE case, but if you also look at large scales, then there should be some universal stochastic description of this model. So one thing that's apparent in this model is that you merge vortices and you create larger and larger structures. And that was absent in the original Arnold-Cat problem. So we said we're going to modify it so that we allow the creation of larger and larger scales. Okay, and so what I'm going to consider is a model in which we allow the creation of larger and larger scales. These are going to be the new modes that arise. And just like in the work of Székelyhidi and Rebekis, we're only going to put randomness into the very initial data of a very general sort, that it should have uniform, it should be absolutely continuous with respect to Lebesgue measure on the torus.
So you're trying to make large scales created so it's like 2D turbulence?
Yeah, so it's exactly supposed to be like this. And in fact, as I'm, pardon? That's right, there's an inverse cascade. And you can see visually that these vortices merge and you get larger and larger scale structures. That was not present in the original Székelyhidi-Rebekis model. Also, I mentioned in passing that the Székelyhidi-Rebekis model does have exactly the same scaling symmetry as the vortex sheet problem. So if you look at the space-time scaling of that initial value problem, the original version of their model has exactly that same space-time scaling. So we wanted to invent a toy model with all the chaotic dynamical properties built in, so we could see if you can in fact get out an effective stochastic dynamics from a renormalization group argument. So by the way, this is not so necessary, but also to make it a little more realistic, we said, well, in real turbulence, not only so in the original Székelyhidi-Rebekis Arnold-Cat, the modes only interacted in a way that you could go up. So you only had segments like this. We said, well, you should also be able to interact down. You could have a small scale that's created by another small scale and a large scale. That's not so important. The results that I talk about don't depend on that, and it could go either way. But anyways, we allow that two-way coupling up and down. The really crucial ingredient is at these particular times, we allow a new large-scale mode to develop out of the mode at the same time at one scale below it, and at that same scale below it at the earlier time. Okay, so the earlier time in this sequence. And as you go on, you just successively develop larger and larger scales through this kind of inverse cascade process. So the precise law that we use is, again, this coupling through the Arnold map. This is our three-way coupling that we use for any given point. This is the two-way one that we use to create those large scales. And this has all the same symmetry properties as both the Kelvin-Helmholtz unstable vortex sheet and the original Arnold-Cat model that they looked at. So what is the idea here? The idea here is that as we add these successive, as we evolve in time, the idea now is, like in the work I discussed with Dima Bandak, you want to integrate out early times and rescale, but here we also want to integrate out all the higher wave number modes, all the small scales, and we're only going to keep a fixed set of low wave number modes, okay? So we're going to try to get an effective dynamics for that fixed set of low wave number modes. Well, you can see from the diagram, well, here we're thinking of this bottom rung in the dynamics as being subgrid modes for this sort of two, we're keeping sort of these two levels here. This set of modes here are the starting subgrid modes, and then we have initial data here, and we want to keep evolving, and then we look at this new block. Now this is new initial data, and these blue ones are new subgrid modes. Then we rescale that back to the starting point. Here, we've now added one extra layer, and we just keep repeating that. Okay, so this is the renormalization group transformation for this problem. And what you can show is, in fact, that this does converge to a fixed point. And in this fixed point, all of these modes, the red ones and the blue ones, become IID uniformly distributed over the torus. Okay, and the proof is a modification of the monotonicity. So people that have read the original Arnold-Cat problem knows that a basic feature was that they had a certain monotonicity in the lengths of the paths to reach each of these separate points, so that there was a very nice ordering. And that, together with the very strong hyperbolic properties of the Arnold-Cat map, were the crucial features in their argument, and we basically steal that idea from them and apply it in this context. By the way, I don't have to look just at this red box here. I can, in fact, extend it outward to allow creation of new modes. I can go out any finite amount of time. And so I get a new effective dynamics for any finite amount of time that I would like to evolve, in which I know the effective initial data and the effective subgrid modes, which then gives me a asymptotically exact stochastic model to calculate the large-scale dynamics. Okay, so Scott, we don't disagree at all. Okay, so in fact, there's no inconsistency in talking about the spontaneous stochasticity and some effective stochastic dynamics of the large scale. They're really mutually compatible. In fact, you can understand one by going back and forth to the other. Okay. We had a little private discussion about that. So again, here I'm actually just saying again, the RG transformation in more detail and what the final result is. And then this is all, this has been, Lowen is writing this up for his thesis, and then we'll put it into a paper. All I want to mention is that exactly the same RG approach can be applied to the Kelvin-Helmholtz case, and this is something that we plan to do. This will have to be done numerically, of course, because we have absolutely no understanding of the kind of ergodic properties that would be required to prove this. I mean, we'll see, but I mean, I'm not confident we can do anything analytically, but at least numerically you can try to do this also for the Kelvin-Helmholtz case numerically, and in that case you have to evolve in time, rescale the initial data back. That creates smaller scale eddies, which you then have to coarse grain out, and you have to come up when you get this new effective term. That's the new term that's created by the coarse graining, the renormalization group, the block spin. And you have to come up with some ansatz for that, and then try to get a fixed point under the successive rescaling. Okay, so in principle, this can be applied to more realistic problems as well. Okay, so let me talk also about some other intellectual connections of spontaneous stochasticity. This connection was something that was suggested to me already by Krzysztof Gawędzki when I first met him in 1997, and he told me about this idea of spontaneous stochasticity, and he had this very clear idea that spontaneous stochasticity is very similar to what happens when you have many non-unique ground states with some distribution over them. And the way you can understand that formally is by taking, for example, a stochastic equation of this type. It could be, ODE, formally a PD if I consider something like Landau-Lifshitz equations, although as I tried to argue, that's really just a large set of stochastic ODEs. And then you can write this, the solution of this for transition probabilities in terms of some path integral with an Onsager-Machlup action. Okay, now if there is spontaneous stochasticity, then the limiting solution as epsilon goes 0. There should actually have been an epsilon here. I forgot to put it, sorry. So the limiting solution as epsilon goes to 0 won't be given by steepest descent. Instead, it will be some superposition over the non-unique solutions of the limiting singular initial value problem.
But now I'm confused because, I mean, this ODE
I mean, the limiting stochastic process, why is it helpful to describe it as a solution of that ODE? Because that ODE the solutions could be dense in the set of all trajectories.
You're saying, why do I know that I'm supported on solutions of that
In
ODE?
some sense, it's a weak solution. I guess I question the usefulness in describing the limiting process as a weak solution like that. I guess in the same
I mean, I would say that is the basic idea of spontaneous stochasticity, is that this happens, right? And so,
I believe there's a stochastic process and that you could describe it. I just don't believe that this description is.
well,
Yeah, okay.
what can I say? Maybe not. I mean, what I will try to suggest is that this point of view makes very interesting connections with other problems in statistical mechanics. And those other connections with other problems in statistical mechanics could be very useful in understanding this problem. That's what I'm going to argue. Okay? We'll see. I mean, maybe you're right. Maybe it won't. Maybe it'll turn out to be a dead end. But I would say this is the essential idea of spontaneous stochasticity, is that the limit is some random distribution over solutions of some non-unique solutions of some singular equation. That's what spontaneous stochasticity
Our
is.
trajectories are going to be nowhere differentiable, right?
Pardon?
Our trajectories are going to be nowhere differentiable.
Okay.
This is some very weak.
That's right. This is some weak solution. That's right. This is some,
And I'm
yeah.
suspicious that the weak solutions of that might be all trajectories.
Well, with some specified distribution
Or
over
it'll
them.
be dense in the set of all trajectories.
Possible, but with some well-defined distribution over them.
Yeah, I mean, it has a law.
Yeah, great. Actually, I don't think it'll be all of them. So for example,
Maybe dense.
pardon? Well, for example, I mean, we didn't prove this, but I conjecture it's true for the Landau-Lifshitz case. We only proved that the probability measure is supported on weak Euler solutions. But I think with using large deviations estimates, you should be able to show that it's supported on dissipative weak Euler solutions. Because we know that the probability of seeing, anti-thermodynamic behavior is exponentially small. And as that noise term disappears, you should be able to use large deviations to show it's not just supported on any weak Euler solution, it's supported on a special class of them. By the way, I mean, I think, in fact, energy alone is probably not nearly enough, because we know the Navier-Stokes has many special properties, like the Constantine-Ear or Kelvin theorem. I think, I mean, the limiting Euler solution should know something about the Kelvin theorem. But anyway, so I think that those are going to be, my guess is they're very special Euler solutions that they're sitting on. Okay, but anyways, this is the meaning of spontaneous stochasticity, and then you can say, is it useful? I mean, there was a question asked to Michael Faraday when he first lectured about his work on magnetic induction, his experimental work. And he gave a public lecture, and somebody in the audience raised their hand, and they said, what use is this? And Faraday's immediate response was, what is the use of a newborn baby? Okay? Yeah, you don't know what the baby is going to grow up to. So yeah, I cannot say anything other than what Faraday said.
Spontaneous stochasticity is not, there's a limiting stochastic process that's non-degenerate. The theorem for you is, and it's supported on these.
That is the essence from talking with Krzysztof, and that was his view. That's what they define spontaneous stochasticity, is that you get a limiting distribution and it is supported on some non-unique solutions of some limiting, some non-unique weak solutions of some type, of some limiting singular dynamics. That's spontaneous stochasticity, by definition. And if you see something else, it could be very interesting, it could be very important, it could be very relevant, but that's what it means. Okay. Unless you change the definition of what the originators had in mind. So it could be there are more interesting concepts. Pardon?
I would change the definition.
Okay. I mean, make your own definition, and this is always fun intellectually. We can have competing concepts, and then you see the best, which is the best one that wins. That's fair science.
From the physical point of view, we want to believe also that the epsilon, the noise, we select some stuff among all possible trajectories.
Yeah, the noise and the regularization together, done in an appropriate large universality class for suitably, chaotic dynamics, will select some universal thing, like happens in the Krykinen model. So in the Krykinen model, we know this does happen. Of course, there you're building in stochasticity by hand, but we know in that case that exactly, it doesn't matter how you regularize, it doesn't matter how you put in external noise, like noise in the initial data, you always go to some robust, universal, spontaneous statistics of the Lagrangian trajectories. That's the vision. Whether the vision is real, well, we'll find out. Okay, but what I did want to say is that you can understand this then using tools from statistical physics and field theory, and and also, by the way, probability. Probabilists would do the same thing. If you want to understand this limiting statistics, you can do it in terms of generating functions. So you can look at the usual generating function, or you can take its log, and then you can look at cumulant generating functions. This J is just the term that you use to take functional derivatives so that you can get averages of any order. And then you can take a Legendre transform, and there are different names for this in different communities. This is what field theorists call the effective action. Probabilists also do this exactly same thing. For them, this would be the Cramer large deviation rate function. So that means that if you repeat the solution of this equation many times for different samples of the noise, and you do that n times, you would create an n sample average of paths, and then this would be the large deviation rate function for that empirical average. And that's the meaning that probabilists would attach to this. It's the Cramer large deviation rate function for n sample averages. So many different communities study this quantity from different perspectives. Okay, so what I want to just explain briefly is that if you use this definition of spontaneous stochasticity, which I think is the canonical one since it comes from the originators, and we'll see what the Armstrong version is. But anyways, if you use that canonical definition, then you can directly show that the limiting effective action has a very simple form. You have to calculate it from the relative entropy. So P is that limiting measure that I talked about here. And Q is then the relative, Q is the relative, oh, I don't see it, that's interesting. Oh, there it is, okay, it didn't switch, it switched on my screen. So then Q is the relative entropy of measures with respect to P, defined in this usual way. And then you can show that this effective action is just given by the infimum over all Q that give the average over the trajectories, which is that given Y, and then this infimum is taken over that relative entropy. This is not a hard proposition to prove. Anybody that knows a little bit of large deviations theory will know that since this is the Cramer function, I can also actually from n samples make an empirical measure by just taking a delta function at each particular realization and then taking that n sample empirical measure. And then this H is the large deviation rate function. It's the Sanov theorem large deviation rate function for those empirical averages of those IID samples. And so therefore, this result follows immediately from the Sanov theorem and the contraction principle. Okay, but what it does tell you is that this limiting effective action encodes all the information about that spontaneous statistics. You can read off what the limiting spontaneous statistics is from this effective action in a very simple way. Okay, by the way, when I defined it here, remember, or know if you didn't know it before, that when Q is not absolutely continuous with respect to P, then this thing is infinite. And in fact, as I will show you, this thing tends to be quite singular. So let me show you what it actually turns out to be for that minimal ODE model that I investigated using renormalization group methods with Dima Bondak. So in that case, you can calculate it. In fact, it's just an application of the theorem that I just showed you, so the general theorem. So remember that in that case, we have this dynamics, which is a regularization of that standard ODE example of non-uniqueness without Lipschitz. And the limiting spontaneous statistics is concentrated on just two extremal trajectories. And the two extremal trajectories are given here like this. And depending on how I took the limit, I get probability p for the x plus and probability 1 minus p for the x minus. This is not very robust spontaneous stochasticity in this model. It doesn't depend on the subsequence, but it depends on exactly how I regularized the problem and how I took the initial data. Okay, but anyways, if I apply that preceding theorem, this is what pops out. And the first thing is that this y is infinite if you are not in the convex set, the set of convex combinations of those two extremal solutions. So this effective action is extremely singular. Okay, it's very singular. It's infinite if y is not a history, which is a convex combination of those two guys. And then inside that convex combination, it has this exact formula, and that's the exact effective action for the spontaneous statistics of that simple toy problem. Okay, now, if anybody knows a little bit of statistical mechanics, this looks very familiar. And the thing that comes rather immediately to mind are equilibrium systems with infinitely many, or with non-unique ground states. They don't have to be infinitely many, but with non-unique ground states. So there are many types of examples of that. One of them, which everybody knows, is a simple, elementary textbook example, is the one-dimensional Eyink model. So here I've actually written the Eyink model Hamiltonian in a way to make even more striking the similarity to my Onsager-Machlup action by having the square of the dynamics here. This is equivalent to the usual formulation of the Eyink model, but makes it even a little bit more clear, the analogy. So you can think you have an effective dynamics of transferring sigma along the lattice spacing. But anyways, here's the standard one-dimensional Eyink model. And you can define it has two ground states in the zero magnetic field, infinite volume limit. And it's either all spin up or all spin down. Those are the two pure ground states, the ergodic ones. And then you have arbitrary mixtures, convex mixtures of those, but those are the ground states for the system. Okay, now you can look at the Helmholtz free energy for this model, the Gibbs free energy. As everybody knows, they're exactly soluble in this case, using transfer matrix, for example. And you can explicitly calculate them in the zero temperature limit. Notice that the zero temperature limit is like the zero noise limit in our dynamic problem, because zero temperature appears here just like the inverse of the noise appears here. Okay? And then what you see is that the free energy comes out to be this, the Gibbs free energy. So this is the analog of that W that I wrote. G, which is this Legendre transform, is the analog of the effective action. And this is what everybody knows, even that has studied a little bit of statistical mechanics, is that limiting free energy is extremely singular. It's infinite unless you're in the convex set between -1 and 1, which consists of the two ground state magnetizations. And it's zero there and infinite everywhere else. Okay, so I think everybody can see the very close formal analogy between the spontaneously stochastic case and this simple example of a Hamiltonian system with non-unique ground states. There's a very clear formal analogy. Now, one question is, can you actually use that formal analogy to any benefit? One thing you can try to do is, we know that there are renormalization group methods developed in physics for calculating the effective action. So in principle, as Wilson explained, you can convert the problem of calculating a partition function into a dynamical systems problem. And the same thing can also be done for this effective action. And you can, in fact, this is very closely related to the work that we heard about the many different fixed points of KPZ. It's the same kind of technology. The only difference here is that, as in the case of the work with Dima Bandak, and unlike critical phenomenon, the universality that you expect is not independence of small scales, it's independent of the details of the initial data. And so what we do here is we introduce a regularizing function, not in order to eliminate small scales, although if I wanted to do it with coarse graining, I would do that as well. But here, I'm just, in this toy problem, considering integrating out the early times. And then that's what this regularizer does. By the way, for people that are mathematicians, I can tell you there's a very simple probabilistic interpretation of this Wederick-Morris flow equation. I don't think, it's never been discussed in the literature as far as I know, but essentially it's applying Bayes' rule in reverse. And so you can think of this regularizer as you're taking measurement errors of the field, and what you do at the beginning is you take very, very accurate measurements of every degree of freedom in the system, and then you know the initial data perfectly. And what this Wederick-Morris FRG flow equation is, it's taking that Bayesian conditional statistics with less and less accurate measurements on more and more coarse-grained variables, and it's successively removing the information of the measurements. That's what this FRG flow equation is doing in the probabilistic sense. That's exactly equivalent to the standard view in the field theory literature and physics literature. So that's, for probabilists and mathematicians, that's what it means. Okay, so in principle, by solving this FRG flow equation and doing the same kind of rescaling, you can also look at this limiting effective action and get a fixed point and understand its universality. This is much more powerful because now I no longer need Markovian dynamics. I can do things like add a fractional Brownian noise, and I can do this now in a completely non-Markovian setting with long-time memory, which is also very important for climate, because we know that climate noise is definitely not white noise. There have been lots of empirical studies. It's some kind of colored noise. And so if we want to have any kind of realistic, by the way, this is an interesting point going back, every example that I know of the fine-grained spontaneous stochasticity without coarse graining is Markov. So this is true of all the rigorous known examples of which I'm aware, is that when you look at the fine-grained distribution on those singular solutions, not only do you get a random process, it's a Markov process. But when you do this coarse graining, of course, then it becomes non-Markovian. So actually in the toy problem that I looked at, unfortunately with the Arnold cat, it's Markovian because all the noises are IID. But in any case, in general, you don't expect it to be Markovian. Okay, so anyways, you can try to solve this FRG flow equation, and in fact, I tried to do that already like 4 years ago. We started to do this with Leonie Canet, and we made a little bit of progress. We've never published this because I'll tell you in a minute what we're still stuck on. But you can follow exactly the same strategy that I did for the Markovian case driven by white noise, but now you do it with fractional Brownian noise with some Hurst exponent. So now, in addition to having the Holder exponent of the velocity field, you also have some Hurst exponent of the fractional Brownian motion. You shouldn't confuse them. But you can follow the same strategy. And now when you rescale, you have to solve this new equation, and this is the thing that you need to do. This implements the rescaling. This is the type of typical equation that you actually need to evolve to get a renormalization group fixed point. We never came up with any successful method of numerically solving this equation. Still have not to this day. None of the standard approaches, ansatz, made any dent on this. Matthew and I are still working on this, in particular with Human Awadi at Caltech, who says, I can solve any functional partial differential equation. And so he says, okay, I've got one for you. So we're trying some of his stuff. Okay, so the underscore just indicates that I've rescaled things. So as usual, when you're doing renormalization group, you don't just coarse grain, integrate things out to get a fixed point, you also have to rescale. That's when you get a fixed point. So like when you do the block spin, the Kadanoff block spin, you just don't make a block spin, you rescale it. And in fact, that rescaling is crucial because when you have an anomalous exponent for the correlation, there's a non-trivial rescaling exponent. The field theory renormalization gives you another critical exponent, which is non-trivial, and that has to be figured out self-consistently. Okay, so that rescaling is an essential part of the renormalization group approach. In this case, by the way, we don't have to have an anomalous exponent, so it just comes from dimensional analysis. So the real point is that what we expect is that you get this kind of divergence with some power, and the particular sigma depends on which particular trajectory you're looking at. So in fact, if you're looking at the extremal trajectories that are the only ones left, sigma 0. If you are looking outside the range of those extremal trajectories, then you get standard Friedland-Wenzel scaling. But if you look in between them, then it's known rigorously for this model that you get so-called singular large deviations that is distinct from Friedland-Wenzel, and that corresponds to sigma equals 1. Unfortunately, we have not yet been able to derive this from this equation. I apologize. We tried, and we're still working on it. What we can do is take this ansatz and plug it back into that equation, and then it's very straightforward to derive in the language of statistical physics a Whittem scaling relation for this factor here, this function here. And this says that the large deviations rate function for this problem must have a particular scaling property. That we checked by brute force numerical simulation of the stochastic ODE driven by fractional Brownian noise. And what you can see is that when you rescale according to the prediction here, that at very high Reynolds numbers you do collapse. So this is a verification that we are getting this kind of rescaling. And we looked at two different cases. In this case, you have the so-called singular large deviations. And by the way, the rate function appears to be essentially the same as what Dima, Bondak, and I calculated analytically for the white noise case. So in this range of Hurst exponent, the long-range memory in the noise doesn't appear to change the singular large deviations at all. Here, however, it does change, and then you see standard Friedland-Wenzel large deviations. In fact, whenever in this case, whenever we chose h equals 1, little h, the Holder exponent 1/3, then Hurst exponent 1 is the crossover point. And then you again get the scaling relation is verified, but now it's standard Friedland-Wenzel. Okay, so the singular large deviations disappears above some critical Hurst exponent. By the way, there's an even larger critical exponent where it's no longer even spontaneously stochastic. So you have different transitions, thresholds that appear. For statistical physicists, this is obvious. They'll say, well, of course, if you change the range of the interaction, you'll change the universality class. Okay. Now,
So capital H is the one of the...
that's the Brownian motion, yeah, the fractional Brownian motion. And little h is for the velocity vector field.
So how do you always pick capital H bigger than...
No, so I mean, this is below, this is in the range of Hurst exponent where you have singular large deviations. And this verifies the scaling relation in that range of singular large deviations. So you'll notice that the scaling here is actually with a different sigma than this one. This sigma is 1, which corresponds to the singular large deviations. This sigma is actually the inverse of that power, so that you end up getting the probability is decaying like exponent of minus Reynolds number, which is the Friedland-Wenzel scaling. But in both cases, this Whittem scaling relation is verified. We did not do numerical simulations. Well, Combe did a little bit of numerical simulations in the regime where you don't even have spontaneous statistics, but that's kind of less interesting. But anyway.
And small h, how much is it?
Pardon, our little h was 1/3. So we decided to do the same case that Dima, Bondak, and I did. I mean, the Kolmogorov value. Okay. Okay, but,
Surprising when capital H is bigger than 1, that the behaviors are very different.
yeah, they're very different. So when capital H, and again, for every little h, there's a different critical big H. But for little h 1/3, the division is capital H equals 1. That's the critical value. And above that, the singular large deviations disappears. And then if you take even a bigger capital H, eventually the spontaneous stochasticity disappears. Okay.
I mean, it's very smooth.
Pardon? Yeah, it's very smooth. Yeah, very smooth. Somehow it's more correlated, and that destroys the spontaneous stochasticity. Okay, anyways, I don't want to, let me say, okay, so, but this is very simple. Statistical physicists know that there are many more interesting examples with non-unique ground states. Probably the most famous is the Sherrington-Kirkpatrick mean field spin glass, where you have replica symmetry breaking, and it's known rigorously now that indeed you have infinitely many ground states in that model, in the mean field model. Okay, so this example is very simple because even though there are a continuous infinity of non-unique solutions to that ODE, the spontaneous statistics only selects the two extremal ones. If you look at the picture that I showed you with the statistics coming out of the shell model computation, it is definitely not just two spikes. We had a whole continuous family of probability distributions that seem to appear in the infinite Reynolds number limit. So it looks like that in that case, we don't just have one solution in the support of our measure, but a whole infinite set, whether countably infinite or uncountably infinite, who knows? Okay, so then you can ask the question, and especially if you're my collaborator Nigel Goldenfeld, Nigel said, this looks like there could be replica symmetry breaking. Okay, so we checked it. And this is work that has so far only appeared in the PhD thesis of Dima Bandak. And I would say it's still very conjectural. There are a number of things I'll tell you that should also be checked. But we said, well, there's a very simple way of looking at this as a spin system. And this goes back to work of Bensi, Buffarelli, and Parisi, who showed that you can write the shell models in terms of multipliers. And so you have these Kolmogorov multipliers, their logs are like real valued spins. And these are the so-called phase multipliers, which are U1 valued spins. And Parisi and colleagues had actually conjectured that the invariant measure for the shell model dynamics, this is the single time measure, is actually a Gibbs measure with a short range interaction for these spin variables here. And so this has been checked numerically and it looks like it works. And so we said, okay, there's a natural set of spin variables for these spontaneously stochastic trajectories. And therefore, we can look at the possibility of replica symmetry. We can look at the overlap. And so what we did is we took sigma and tau are now representing different independent noise realizations. So remember, we're creating a whole ensemble of solutions of our shell model. Every solution, because we're doing everything at large but finite Reynolds number, we have strong stochastic solutions in the model. So for every specified noise realization, there's exactly one solution. And so we have this whole big ensemble of solutions of that noisy shell model. And we can say, okay, let's look inside the inertial range of that model. And we can calculate, actually, I shouldn't have done it this way, I guess. This is a little, I'm sorry, I forgot to do this. This should really be stated differently. I forgot to change it. This was Dima's original side. I have a time average. That's not the right way to look at it. Something I didn't tell you about this model is because of scaling symmetry of the model, to take the infinite Reynolds number limit, the easiest way of doing that is to integrate to longer and longer times and rescale. And it turns out that's equivalent to looking at the high Reynolds number limit. So what I should really be doing here is having a fixed time, but take the infinite Reynolds number, the limit of infinite Reynolds number. And when you do that, you can look at the overlap between these spin variables. And here I'm just showing you the final result. It looks like in the infinite Reynolds number limit, we get very nice non-trivial overlap distributions. By the way, this is not trivial because even at the very astronomically high Reynolds numbers that we looked at, up to 100 million, we don't get good collapse. I'm not going to show you the collapse, but if you want to see it, it's in Dima's published thesis. We had to do a finite size scaling analysis to get these collapse distributions, but I think we did it quite convincingly. And so it looks like in this model, in fact, there is a non-trivial overlap in these spin variables. So this suggests that there's some kind of hierarchical organization of these non-unique solutions. There are many obvious directions that have to be pursued here. For one thing, you can try to see, does this define an ultrametric structure on those non-unique solutions? Okay, so is there some natural ultrametric structure of this set of non-unique solutions which is in the support of this measure? Okay, so Scott, that's the kind of things that we hope will be fruitful. Okay. But again, this is only supported by this one numerical experiment, and this is stuff that's still ongoing. In particular, in principle, we can use the overlap to actually calculate the ultrametric. And in the limit of larger and larger Reynolds number, you can check to see whether the ultrametric triangle inequality is satisfied. If that's true, then we will have strong evidence that in fact there's an ultrametric structure of the support of this measure. Okay. By the way, if that's true, it also means that there is a nice connection between the work of Hasselmann and Parisi, who both won the Nobel Prize in the same year. And it turns out that their works are actually intimately connected with each other. So that's a fun thing. Okay, now let's turn to something which is very dear to my heart, experiment. Okay. It is actually a bit of a scandal to me as a physicist that we have no convincing direct evidence of spontaneous stochasticity from even one laboratory experiment. The only indirect evidence we have, I showed you on the very first slide of my talk, and that's the evidence for anomalous dissipation of the scalar. And those are from experiments that were done by many people, but among other things like in turbulent jets, in wake turbulence behind a grid. There is no solid boundary once the turbulence was created. And so you're looking at decaying turbulence downstream, and what we have is, that is the available evidence that we have, is that if there is a dissipative anomaly for the scalar, that requires Lagrangian spontaneous stochasticity. But as I said, for more than 20 years, experimentalists have been trying to see Lagrangian spontaneous stochasticity of particles in the lab and have failed. Okay? It has not yet been seen. So you would like to say, can I actually observe this in the lab? What are the opportunities of seeing this experimentally? Pardon? No, I mean really quantitatively verifying, for example, that when you let the particles get closer and closer together, that you bend over to the same Richardson dispersion and you forget the initial separations of the particles. That has never been seen experimentally. Okay? It's been seen by Jeremy and others in numerical simulations, and it looks like it's simply a technical problem. Right? Because, as I said, it's just very, very hard to track individual pairs of particles when they're densely seated in the flow and say, what is the, I have two pairs, I have to say, what is their distance in time? And I can't confuse this particle with some other particle that crosses close by it.
Paint one blue and one red.
But you need to have large statistics. And so you need to average over many of those pairs. You can't just put them in one by one, that would be hopeless. So, I mean, you talk to any of the experimentalists about this that study Lagrangian paths, they've been trying hard for decades, and they have not managed to do it. I have an actually interesting story that involves Jeremy that I can tell you privately about that.
Michael Bourgoin keeps telling me that there is a recent experiment by maybe Jeremy, of a Chinese group doing experimental stuff, and they have seen the Richardson.
Well, there are many people that have claimed to see Richardson. That's Ott and Mann.
Experiment?
Yes, in experiment, Ott and Mann claimed to see Richardson. There are lots of people that have claimed to see Richardson. That's not the point. For example, you can have many things that produce T cubed. If you look in turbulent shear flows, Stan Corson many years ago showed that if you look in a turbulent shear flow, pairs of particles separate according to a T cubed law. It has nothing to do with spontaneous stochasticity. And in particular, in that case, yes, you see a T cubed, but as you let the initial separations get together, they all collapse to one trajectory. The crucial thing is not T cubed. The crucial thing is that you get the same result even as you let the Reynolds number get larger and larger and the particles get closer and closer together. That's the crucial thing. Oh, just like a flow in which the velocity is high here and then it gets lower and lower. So there's some shear. Actually, the Kelvin-Helmholtz unstable vortex sheet is a shear layer. Okay, because you have a shear this way. But I mean, if the velocity is simply changing, then that's a shear. Okay. Anyway, so again, there are many things that could produce T cubed in a turbulent flow. Like you see that T cubed law in the boundary layer of channel flow, and it has nothing to do with Richardson and nothing to do with spontaneous stochasticity. Okay. But maybe Eulerian spontaneous stochasticity opens up some new opportunity. By the way, how much time do I have?
You have, so that's my job. You have 20 minutes.
20 minutes, okay. I think I'll finish in plenty of time. Maybe we can even get out early. I think there are some new opportunities that are opened up by the Eulerian version. And in particular, I want to point out that the whole concept of spontaneous stochasticity is very closely related with very old ideas for things like wake turbulence that go back to Townsend, who already in his 1956 book had postulated that for turbulent wakes, there's a universality of all high Reynolds number turbulent shear layers. So these are things like the vortex sheet and wakes behind bluff bodies. And he said that you should always go to a self-similar state for getting the initial data except through conservation laws, mass, momentum, and energy. And this is very intimately connected with the idea of Eulerian spontaneous stochasticity. In fact, the example that I showed you with the Kelvin-Helmholtz unstable vortex sheet is a very simple example of Townsend's universality hypothesis. Okay, it's a very simple toy example of it. And these hypotheses have been extensively investigated already experimentally. So I guess one of the messages that I want to say, whenever you're talking to your experimental colleagues, it's always hard to get them to start something new because they want to investigate the old questions that they know. So if you can tie this phenomenon to something they're already studying, then you already can have an extensive literature to refer to and so forth. And all of these issues of forgetting the initial data, universality, self-similarity, all of those are being extensively investigated already. Since these works, by the way, when I first told Srini about Eulerian spontaneous stochasticity, his reaction was, well, of course. What else could happen? That's exactly what Townsend predicted. And I think, yes, that's true, but Townsend didn't explain why. Okay, it was just a hypothesis. So what we want to understand is the dynamical and statistical basis of this universality if in fact it does occur. So I mean, again, there is a lot of investigation of this up to the present time. Here I cite one, not so recent, 13 years ago, but they have a nice bibliography and they discuss all of the previous literature. One thing that you will find from reading this paper, which I very much recommend, by the way, these figures are taken from that paper. And what they started off with different initial data. So I don't know, Jeremy, if you know this paper, but they started off with different kinds of initial data that have the same mean profile. One of them was a vortex ring, so you have a set of vortex rings. And another one was a homogeneous distribution of vorticity, but with the same mean profile as produced by the vortex rings. And then they looked at both of those cases and they tried to see, do you go to the same asymptotic self-similar state, independent of what kind of initial data, et cetera, et cetera. Very much like what you did with Thalabard for the 2D problem. And here you can actually see the successive growth in time of this shear layer for that particular vortex ring configuration. By the way, I should say that Townsend's original hypothesis was not for this kind of development in time. He was originally thinking of the spatial development of a wake behind a body. So he was thinking if you're sitting here, you have some like a sphere, and then you have a spreading wake. And so he was actually thinking of, if you like, self-similarity in space. But it has been widely hypothesized that that's equivalent to this kind of self-similarity in time. And indeed, there's some ambiguity about whether the wake is a Eulerian steady state, or if you're moving with the fluid, whether it's time-dependent decaying turbulence in the Lagrangian frame. Okay. But anyways, so all of these different questions have been investigated. What you will learn from reading this paper is that there have been a lot of observations that you don't forget the initial data. Okay, there have been a lot of observations that you do not forget the initial data. Okay, but what they showed here, using numerical simulations with an adaptive grid, coarsening it with time so they could go to extremely long times, they found that if you go to long enough times, then yes, you do forget the initial data, and you go to an asymptotic self-similar state, and it doesn't depend on the details of the initial condition at all. Okay. So I think that this is one nice opportunity to interact with the experimental community on this problem. But this is not the only way to do it. I should tell you that in the case of the shell model, what I showed you was data for the Kolmogorov initial data, that stationary unstable Kolmogorov solution, but we also picked out native solutions from the statistical turbulent steady state. So we have a long time statistical steady state for our shell model, and we can just pick out native realizations from that. And we can also add little perturbations on those and see if they exhibit spontaneous stochasticity, and they do. It's not as nicely self-similar as it is for the Kolmogorov one, but they do exhibit spontaneously stochastic behavior. The presumption is if you average over a lot of those initial data, you'll restore some kind of self-similarity, although it might be multifractal or something else. But that same kind of thing can be done experimentally. Now experimentalists have remarkable capabilities in terms of measuring full 3D velocity fields to high resolution. So for example, my JHU collaborator, Joe Katz, is a master of this, using holographic PIV. They can do amazing things. So in principle, you can have nice interactions between numerical people and experimental people. They can actually give you a snapshot. The technology is developing where they could give you a single snapshot taken out of a turbulent flow, and they say, put this in your numerical simulation, evolve it with little random perturbations, and what happens? Does it exhibit spontaneously stochastic behavior? They could give you a sequence of those at higher, yes?
But in 3D simulation, and all the simulation that are here in here are 2D.
Yeah.
I'm very sorry, there is a major difference. All the, 2D and 3D has nothing to do.
Oh, definitely.
Vortex stretching.
Yeah.
And all the odd and even dimensions are very different.
Oh, no, I'm not talking about going to high dimension.
No,
Yeah,
but 2 and 3D.
Yeah, 2 and 3 are yeah, no, definitely 2 and 3 are extremely different. Well, in fact,
it's not the same than 6.
yeah, in fact, I would say that the oddest of them all is 2. The oddest of them all is 2, because all the other ones have some version of vortex stretching, and the 2D one is the most degenerate case.
Completely degenerate.
Yeah.
And if you have good data from CAM, please go to 3D.
Yeah.
I can give you some, there are some very good data in this simulation. 3D is very large Reynolds number, billions of particles transported, ego.
By the way, these are not only interesting. Yeah. By the way, these are not only interesting intellectual problems, but they're of real practical interest, because there are people all over the world now trying to do data assimilation, applied to turbulent flows, to reconstruct from experimental data the actual true velocity field. Well, if there's spontaneous stochasticity and you have limited data, in the high Reynolds number limit, it's no longer even clear what you mean by the actual true velocity field. What you actually probably want is a statistical ensemble. And so this actually enters into very practical issues that are being investigated. Yes, you had another remark.
What methodology has been used for the last 20 or 30 years with data assimilation?
Absolutely. But now, but I mean, so so of course in the atmospheric sciences, it's very common, but it's starting to be heavily imported into mechanical engineering. Yeah. Okay, so I think those are some opportunities that I think are opened up by this, where we can start to get some more experimental insight. Here's another nice example. This is the Rayleigh-Taylor problem. And in this case, as everybody knows, you have a heavy fluid above a light fluid, and the heavy fluid drops, the light fluid rises, you get this Rayleigh-Taylor instability. And this is one example where without the Boussinesq approximation, with a sharp interface, convex integration methods have been applied, and we know that there are infinitely many admissible solutions of the limiting Euler equations for that problem. So this is this work and other following work after that. This has also been studied numerically by Biffarali et al. This is actually, by many people. This is just one work that shows this phenomenon. They actually did it with not just sharp interfaces. First of all, they used Boussinesq approximation. And they also studied not just sharp interfaces, but somewhat power law smoothed interfaces, or this C could even be negative, so it could be less than smooth. And they found that there is some dependence on this parameter C, but in particular, this paper found in the limit of high Reynolds number evidence for spontaneous stochasticity, Eulerian spontaneous stochasticity in this flow. By the way, I should emphasize that the evidence for spontaneous stochasticity in this paper also required a shell model. So they couldn't do it with the actual Boussinesq equation. They had to, because you couldn't go to high enough Reynolds number. So the evidence that you had spontaneously stochastic arose, just like in our work, from a shell model calculation. I should mention, however, also that there is continued investigation of this. This is actually work done by a group at Los Alamos. The people at Los Alamos, for some reason, are really obsessively interested in Rayleigh-Taylor. I don't know why. Anyway, yeah, okay. I mean, it's just an obsession with them, okay. But anyways, they have published, I just was looking for recent papers that studied this issue, and, pardon? Yeah, there are lots of people that have this obsession. Yeah, it's strange. Okay. Actually, there are going to be more people in France that have this obsession. Yeah, okay. Anyway, but anyways, this group published a very nice paper recently, and again, they found evidence that in this problem, you forget the initial data only very, very slowly. By the way, this is similar to observations that Jeremy saw in SQG, right? So it may be that you don't just have vanilla Eulerian spontaneous stochasticity. You could have also things that are close to it. In fact, Nigel, looking at Jeremy's work on SQG, said, well, maybe you have incomplete self-similarity there. And if you have incomplete self-similarity, you wouldn't completely forget the initial data, but it would appear in a very particular way through an anomalous exponent. So there's all kinds of rich possibilities. You know, nature will tell us what the interesting things are, and so there are still many, many things to explore. Okay. Another really interesting example that's dear to my heart, because I'm very profoundly interested for incompressible flow in the effect of solid walls, And there has been work by Vasseur and Wang. This was actually not, I would say, even the main point of their paper. They were more interested in getting exact a priori estimates without any conditions on Navier-Stokes, and in particular very delicate estimates on vorticity at the boundary. But among other things that they did is they did a convex integration construction that showed you can get non-uniqueness through separation at the boundary. Okay, so this is another possible source of spontaneous stochasticity, is in very, very high Reynolds number boundary layer separation. Here I'm actually showing you stills from a recent paper. So Marie, this is the paper I was mentioning to you the other day. So this is a recent paper that studied the old Prandtl problem from the 1930s, I believe, maybe 1920s, of an impulsively accelerated disk, or they called it cylinder because they're assuming it's 3D cylinder, but with symmetry along the axis. So anyways, it's an impulsively accelerated disk where you start off the disk initially at rest, and then you instantaneously make it move with an impulsive acceleration. From a mathematical point of view, this corresponds to taking the D'Alembert potential flow solution as the initial value for the Navier-Stokes equation. So basically you take the D'Alembert solution and you suddenly turn on viscosity. Okay, and that's what you're visualizing here at a sequence of higher and higher Reynolds numbers. What you can see is that as the Reynolds number gets very large, and by the way, this is the highest published value, but Petros has gone up above 1 million, and he didn't publish it only because his simulations are under-resolved there, and he thought it would be professionally irresponsible to publish under-resolved results. So this was the highest result he considered well-resolved. But in any case, in his simulations, even to higher Reynolds number, there's no indication that the boundary layer no longer separates. By the way, I should mention, this impulsively accelerated cylinder is the origin of the work of Damelin and Chen on the singularity and the Prandtl boundary layer equations. The original paper that you heard about this morning on the Damelin-Chen singularity was for exactly this problem of the impulsively accelerated cylinder. Okay, that's the situation in which they worked and found the singularity. Okay, I'm almost done. This is almost the last slide. Okay, so there seems some numerical evidence that as you go to very, very high Reynolds number, the boundary layer continues to separate. And then this raises the interesting question, could it be that the separation is stochastic? Maybe you don't just have one pattern as you go to high enough Reynolds number, and in particular, if you add in small little random perturbations, you will see not just one pattern, but a whole family, and there'll be some limiting universal statistical distribution on those separation patterns. So this is another very interesting case that can be looked at experimentally. Maybe in astrophysics too. I mean, I think there are major implications for numerical astrophysics because astrophysics has Reynolds numbers that are literally astronomical. And there are so many high Reynolds number phenomena, and I just put some here. By the way, many of them, like the quasar jets and neutron star mergers, are even relativistic, which makes it much more interesting. The goal, everybody in numerical astrophysics is still operating in the Laplacian paradigm. They think you put in your initial data and you'll get one solution out. Maybe that's not the right paradigm. Maybe the right paradigm is more like meteorology. You should not be saying what happens when two neutron stars merge. You should be saying what is the ensemble of possibilities when the neutron stars emerge. So I think this is a very interesting also, especially because the Reynolds numbers are so high, a very interesting direction for future work. Let me just show, why does it always do that? For some reason it doesn't always flip. Okay, there we go. So let me just finish very quickly. I don't want to go into this too much, but I thought it would be fun to end on a really simple example of spontaneous stochasticity triggered by quantum noise. And it actually was something that Theo Drivas was obsessively interested in as a graduate student. And I was having him work on this Burgers problem. And every time I would come into the office, he would take a paper on quantum stuff and shove it under the table so I wouldn't see it. And he was so interested in this problem, I said, okay, finally, let's just do it and get it out of the system. So we did it. And this is an example where you can get quantum spontaneous stochasticity in the semi-classical limit. And it had been investigated previously in the pure math literature, but with a really actual cusp potential. We said, well, that's unphysical. You can't create a cusp all the way to the Planck length and below. That doesn't make any sense. But you can regularize the cusp, and then you can say, in the limit where the mass of the particle, it's really h bar over the mass that matters in the semi-classical limit, where h bar over m goes to 0 and where the cusp becomes more and more narrow, is there only one classical trajectory or more than one? And so we looked at this cusp potential. The limiting singular behavior has non-unique solutions. These are the two extremal ones. And then the question is, what will happen in the semi-classical limit for this problem? Well, as a physicist, you say, well, the semi-classical limit, this is just standard time-dependent WKB. So we did the whole analysis within standard time-dependent WKB. We took an initial minimum uncertainty wave packet. And these are, for the people that know, these are the usual semi-classical, the Hamilton's equations. This is the standard time-dependent WKB. I don't have time to go through this in detail. What I want to show you, what we're going to study is what happens when we let the, start off with this initial data. We're going to take two limits, the semi-classical limit, and then we're going to take the width of this wave packet, sigma, in this minimum uncertainty wave packet to 0. So in the classical problem, you're going to start off exactly at the origin and follow those limiting singular dynamical equations. Okay, so this is what happens. This is for the two different choices of the potential. That doesn't matter very much. But what you see is that when you put that packet at the top, it splits into two things with a bimodal distribution. By the way, this does not happen if you use the so-called inverted oscillator, which has been heavily studied in cosmology. So that played an important role in the inflationary universe scenario, is the inverted oscillator potential. This splitting does not happen with the inverted oscillator potential. It only happens because of that cusp. But then you can do both limits together, and you can say, okay, now let me take very massive particles and let the width of the packet go to 0. And then what happens is if I look at a given fixed time, is that. So what you see is that in the semi-classical limit, starting exactly at the 0, you no longer follow one unique classical trajectory, you follow two. Because there is no unique classical trajectory to follow in this limit. So that means, by the way, that the standard spreading of the wave packet that you learn about in quantum textbooks is violently untrue here. You don't have usual spreading of the wave packet. In fact, you have Richardson dispersion of the wave packet. Okay. And these are just some many connections that I just wanted to mention, but I do want to end with a brief comment about Krzysztof Gawędzki. Okay. So can I just say one word? I just want to say, I think that this gentleman is probably more responsible for the modern understanding of spontaneous stochasticity than anyone else. And as I said, the first time I met him in 1997, that's what he told me about. I became immediately convinced, man, this is an important idea. The last time I met with Krzysztof was on his 70th birthday celebration 10 years later. 20 years later, 2017. So I saw him many times in between, but 2017 was the last time I saw him. And the last thing we talked about was spontaneous stochasticity. And as anybody of you know that knew Krzysztof knew that he had an enormous range of things that he worked on. An enormous range. So he worked very hard in a certain period when he was busy with the Krigman model on spontaneous stochasticity and selling it and saying, this is important, you have to look at this. And then he went on and did other things. So when I met with Krzysztof, I told him about some of the stuff that Theo and I were doing, and I was very proud. He said, well, first of all, he commented favorably and intelligently on all this stuff. And then he also said, Greg, he said, you're keeping the flame alive. What I want to say is that now lately, I have been seeing a lot of new people coming into the field. And I think Krzysztof would have been delighted to see this. And I would just pass on this information to you. He would be so happy that you're keeping the flame alive. So I don't think we can say yet convincingly that there is spontaneous stochasticity. It's still a hypothesis, but it looks like a very intriguing and plausible hypothesis. And I think Krzysztof, if he had been here, would have been very pleased to see that the flame is still burning. So, thank you.